in my red gel.
All right, let's get started. I changed the lecture, so Thursday night. So quite a few of these questions really relate to finishing up today, which we'll do right in. So I backed the quiz up to Thursday night. I'll chapter 4, part 2, which is Friday night, I think. And let that alone. Okay. So let's we'll finish up chapter 4 here. We just got like 3 problems due in chapter 4. It kind of relates to the quiz. I maybe should have said not to do all those quiz questions yet. So, but we're going to set some up here that I have circled at least, and then we'll still do quiz questions on Thursday. And then it'll be due Thursday night. But let's set some things up here a little bit on these. And as it relates to lab this week as well. But 17 here is a limiting problem. So if we look at 17, let's write this out first. It says how much HGS, which would be mercury 2 sulfide. And so it looks like we've got a double replacement reaction. So let's write that out first. Calcium sulfide solution is mixed. So this would be aqueous plus mercury 2 nitrate. I'd better start writing a little bit lighter. So if this is a double replacement, calcium will take the place of mercury. Mercury will take the place of calcium. So we will end up with calcium nitrate. This would be aqueous. Now, caution, 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 caution. It looks like I transferred the nitrate as 2 just over. That is not the case. This, of course, goes by our charges. This is mercury 2, nitrates minus 1.
and calcium is always a +2. Nitrates a -1. I didn't just carry these two nitrates over. It's plus because calcium is +2. Then we are going to get HGS solid. This looks to be balanced. Again, this is a limiting problem, but the nice thing about using milliliters and molarity is you don't need your periodic table. Eventually, we're going to need it. So because we have this final answer here in grams. So let's see what we've got here. We have 113 milliliters. So I'm going to drop this down right here as 0.113 liters. This is 0.75 molarity. This right here is 0.052 liters of solution, the 52 milliliters. And it is 1.21 molarity. So again, definitely a limiting problem. Let's calculate how many moles we have here. Actually, I'm just going to set this up. You can do it. How many moles you need here. How many moles you have. That you can calculate the moles over here and go moles back to grams. 18 looks similar. 18 looks similar. The equation is there. It looks to be a limiting problem. Again, very, very similar. Let's look at 22. Okay. So 22 is what we're going to calculate today with our examples as well. I'll set this up. What concentration of H2SO4, sulfuric acid, solution, if 10 milliliters of the solution is neutralized by 7.8 milliliters of 0.20 molarity sodium hydroxide? So let's do our reaction here first. Let's see, about right here will work. H2SO4 plus NaOH. This is a double replacement neutralization. Double replacement neutralization. So hydrogen takes the place of sodium. So if hydrogen takes the place of sodium, we're fine. Write this in as hydrogen hydroxide, which is water, right? And +1 and -1. Plus sodium takes the place of hydrogen, so we'd end up with NaSO4, and that's going to be aqueous. +1 and -2. So we'd have sodium sulfate like this. And then we would balance this right here. What else would we need? We've got 4. We would need a 2. So we'll set this up, and then after we do the example problems on the learning guide, you'll be able to crank this out. If not, put it on the board next time we meet on Thursday. So what is the concentration of H2SO4? We are looking for molarity. 0.0100 liters of the sulfuric acid. The molarity of the sodium hydroxide is 0.20 molarity and 0.0078 liters. So the very first thing you're going to do is figure out your moles here. And then go to here. And again, after we do the example, I think this will be, you'll be able to finish this one out. Okay, this 23 relates to last time we met. This KOH, strong base? For sure, this is a strong base. So we know without a doubt, 100%, this is going to dissociate into K plus and OH minus. 100% dissociate. I know this is labeled 0.00058 molarity KOH, but there is no KOH hooked up in that solution at all. It is 100% dissociated. And if that's 100% dissociated, I know my molarity of hydroxide is 0.00058 molarity. That I would calculate the POH. You get the pH. I mean, well, actually, you don't have to do it that way. Remember, there's like multiple ways to do it. Looking for the H3O plus, I would do it this way then. That's going to be 1 times 10 to the minus 14 divided by your OH minus concentration. All right, we'll lay out 25. 25 is similar. We've got sulfuric acid again, H2SO4, aqueous plus KOH, potassium hydroxide. And this is going to be, oh, get this up. Lay out 25 here. Double replacement, neutralization. Acid plus a base, we're going to get a salt and water. So again, we would get HOH. And then we're going to end up with K2SO4. +1 and -2 here. So titration, that's what starts today in lab. So titration is just an accurate way to add a liquid solution to another. And again, that starts today in lab. We need to put a 2 here and a 2 here. This is going to be, what is the molarity of the sulfuric acid? This 25 and 22 are too similar. I mean, these are spot on, similar the way it looks. I shouldn't have two problems that similar. So 25 and 22. Very, very similar, 25, 22. Okay, let's go to the learning guide. We're going to finish that up. You're going to see we are doing examples that are going to relate to this. We've got titration problems. So we've got 4 problems to look at. And then after we do those, match them up with what you have left on this quiz. And then we'll put them up there Thursday. And Thursday night, you can submit your quiz. So we left off about right here. We did one owl problem. Let's do example 4.9. So in example 4.9, it says metallic zinc, no charge. Metallic zinc reacts with aqueous hydrochloric acid. This is a single replacement reaction. Zinc is going to replace hydrogen. Zinc has a charge of +2, chloride -1. Hydrogen gets kicked off by itself. This is an oxidation reduction reaction as well, because we have different charges from one side to the other. Now, we want to know how many milliliters of 2.5 molarity HCl it takes to use up the 11.8 grams of zinc. So the nice thing about this is we could pour exactly this many milliliters in there. The zinc would be used up and we're just going to have 100% products. Unlike the last lab we had excess zinc, right? We had excess zinc. So very first thing we got to do, if we're given grams, calculate moles. So let's do that. We'll take our 11.8 grams of zinc. $65.11, I think. 65.41. 65.41. So we have the starting moles here of 0.180. Moles of zinc, 0.180. Right? Now, this is not a limiting problem at all. We're calculating exactly how much we need of the other reactant in milliliters, though. So my mole ratio fraction here is two over one. Yes, 2/1. So it takes twice the amount of moles of HCl. So that's 0.360 moles. Now, I always say start with a single unit number all the time, Start with a single unit number. This is my single unit number now, right? Because this is moles, right? This is moles over liters for units. I want liters of solution. Once I get liters, obviously I can change liters to milliliters. So my question is, when I bring my molarity down, am I going to leave it as is, or am I just going to flip these units? We are going to flip, right? We're just going to flip these units because I have to get moles to cancel out. And the molarity here is 2.50 mole of HCl per liter of solution. And let's do one quick shortcut. Let's cross out liter. How many milliliters? 1,000, right? Let's just put a line through the L and replace this with 1,000 milliliters. Same thing. So if we do the math on this, we should get 144 milliliters of 2.50 molarity HCl. So again, this is the perfect amount. 144 milliliters left over, everything turns into product. Okay, let's go to, here's some acid-base ones. You're doing titrations today. Now, titration, you're going to use the barrettes. You're going to add the exact amount of acid or base. Typically, you're adding base, the exact amount. Everything is neutralized for lab. You have a salt and water. You have a salt and water. And down here, you have a salt and water. So for lab this week, you're doing titrations. You're going to add exactly the correct amount, so there's no excess. So for this first problem, we've got what volume of 0.050105 molarity hydrobromic acid is required to titrate, neutralize 125 milliliters of a 0.0100 molarity calcium hydroxide. So these are quick and easy problems because you don't even need to look at your periodic table. You do not need anything in grams. So the very first thing we're going to do, we're looking for milliliters here. We're going to get moles. So to get moles here, we're going to start with our single unit number. 125 milliliters, 0.125 liters of solution. We're going to bring our molarity down just as is. That is 0.0100 mole per liter of solution. And if we do that, we are going to get 0.00125 moles to start out. So again, these are kind of slick and easy. Don't need our periodic table. We're calculating exactly. So there's no excess. There's no limiting. How many milliliters we need to add to neutralize this base. And my mole ratio fraction is 1. So we have 0.00250 moles of hydrochloric acid. We know that this is in moles. And this is moles, but we always know we have moles there. I want to get milliliters. I'm going to bring this down and I am going to for sure flip this. Otherwise, I'd end up with moles squared, right? I can't end up with moles squared. So I'm putting my 0.0105 mole down below of HBr. My liter of solution on top. Now let's do that same cheat thing because I want my answer in milliliters. I'll simply cross this L out and I'll write in 1,000 milliliters. So for the lab this week, you could calculate out exactly what you are going to add. And unfortunately, I think the lab is 1-to-1. All the ratios are 1-to-1. So it's really super easy to calculate. I think we get, how many sig figs? 3 sig figs all the way through gets us 238 milliliters. Okay. Another example, consider a neutralization reaction with 75 milliliters of calcium hydroxide. Solution is neutralized with 5 times 10 to the minus 2 molarity HCl, or 0.0500 molarity. It requires 36.6 milliliters. We're looking for the molarity. Looking for molarity. So when we get all done, we know for molarity, we need per liters, right? That's all we have to do is get moles over liters. So let's get our molarity here, or excuse me, not molarity, our moles of HCl right here. Our moles of HCl here is going to be, starting with my single unit number, 0.0366 liters of solution. I'm going to bring this down as is. I'm not going to flip this. 0.0500 mole per liter of solution. And my moles is 0.00183. Now remember, molarity is moles over liters, and moles is from grams. So even though you have milliliters here, those milliliters are really dissolved grams. So my mole ratio fraction going this way is 1/2, right? 1/2. So my moles here is 0.000915 moles. And I need moles over liters, right? This is moles. I'm just going to draw my line here. This doesn't have to look pretty. All we need to do is get moles over liters. There's my moles. This is my milliliters of solution. We're going to change this to 0.07500 liters of solution. And right there, I have moles over liters, which is molarity. This comes out to be 0.0122 molarity calcium hydroxide. Okay, so again, we don't have to use periodic tables pretty slick. We are calculating exactly, assuming there's no, in this case, there's nothing limiting. All right. This last one, we're skipping that. It is exactly the same as the one above. It's exactly the same. I don't know why I've got these on here, but this is the same as this one. It's just way too similar. Okay. So that should get you through homework Owl chapter 4, part 2. This is, I think Friday is the deadline. So we'll wrap up this chapter 4. We will take quiz questions yet Thursday. The quiz is due then Thursday night. So make sure you looked at and tried every quiz question, and we'll take final questions on Thursday during class. So that puts us into chapter 5. So chapter 5 is thermal chemistry, thermodynamics, which is heat and work. Heat and work. Okay. First of all, if we describe energy, some of you have had physics, and usually you talk about kinetic energy and potential energy. You don't do a lot with thermal energy, but thermal energy is we need to transfer some heat. So if heat is a form of energy, it ought to be possible to equate it to other forms. Experiment below found the mechanical equivalent of heat by using the falling weight to heat the water. And we would say that this has potential energy, which would be equal to mgh. For those of you who've had some physics, that should look familiar. Yeah, yeah, somebody, yeah, okay, I'm getting at least one vertical knot. Then all of this would be transferred to kinetic energy at the bottom, right before it hit 1/2 mv squared. So I'm just writing this down because energy is in units of joules. This is a mass in kilograms. This is a velocity in meters per second, but it's meters per second squared. So you get meters squared over seconds squared. This gets us a unit of joules. So a joule is equal to a kilogram times meter squared, second squared. That's our units. Now, this is the unit we are going to go back and forth with all the time is calories and joules. Calories and joules. This is a 4. So you're going to go back and forth quite a bit. 1 calorie, 4.184 joules. Okay, heat versus temperature. Again, heat is a transfer of energy from a hotter object to a colder object. Temperature is just a measure of the intensity of heat, not amount. So if you took just a pin out of boiling water and touched it, no big deal. It doesn't contain a high amount of heat energy. If you took something else, a larger object out of there, like if you put a small pan into a large boiling pot of water and took that small pan out and touched it, that would burn because that small pan would have a lot more heat energy than a pin. Another way is a drop of boiling water versus a pot of boiling water. A pot of boiling water has a lot more heat energy, even though they're at the same temperature. And then some language here. System versus the surroundings. So the system, this is the object or collection being studied. The contents of a beaker. Then we can have an open system. On the next page. This is an open system. We are looking at our beaker, we're letting things come out. We could have a closed system if we seal that up. We could have isolated systems. And then we have surroundings, which is just the rest. Okay. Now, some language, and owl, the beginning of owl in this just does a lot of sign convention and really, I don't know, perhaps some nitpicky stuff to get you learning the language. Something is exothermic. Energy is transferred from the system to the surroundings. In this case, whatever's in this beaker would be adding energy to the surroundings outside the beaker, right? Energy out. This is energy out. If heat energy is transferred from the surroundings, that is endothermic. This is putting energy into our system, into our beaker, correct? This flame for sure is energy in. Now, what's the sign convention for this? If it is exothermic, Q is going to be our heat quantity. That's what we're going to calculate. Less than 0, this is going to be negative. For exothermic, negative. Endothermic, positive. Again, this is a sign convention that OWL does in the beginning. So let's summarize again. Endothermic absorbs heat from the surrounding. Heat flows from the surroundings into the reaction. And this is going to be positive heat. Exothermic evolves heat. Heat flows from the reaction to the surroundings. This is going to be negative. Now, another way to look at that is this. If it is exothermic, this will help out a lot. Heat is on the product side. However, it is going to be a negative number. So Q is going to be our heat. Q is going to be negative 100 kilojoules. We calculate this out. If Q is negative, it's going to be on the product side as a positive number. In an energy diagram to look at this right here, Q less than 0. If it is endothermic, notice that heat energy is on the reactant side. We need to put it in as a reactant. Heat on reactant side. And Q, hold on a sec here. And Q is going to be positive 100. So this summary right here should help a lot when you're doing your OWL in the beginning. Again, if we get negative, it's exothermic. Heat's going to be on the product side, but as a positive number. If it is endothermic, we got to put energy into the reaction. It's going to be positive and it's going to be on the reactant side. And typically you'll see an energy diagram like this. So here we have to put energy in. Here we get energy out. Okay. We often speak of heat as though it were a material that flows from one object to another. It is not. Rather, it is a form of energy. The unit of heat is calorie, small c. The calorie is the amount of heat necessary to raise the temperature of 1 gram of water by 1 Celsius degree. That is the definition of the unit of a calorie. The amount of heat necessary to raise 1 gram of water 1 degree Celsius. Now, don't be fooled. The calories on food labels are really kilocalories. So this is a kilo with a small c, right? Or big C calorie. Your food labels are in big C calories, we call them. So that's the heat necessary to raise 1 kilogram or 1,000 grams of water by 1 degree Celsius. Food calories are in kilocalories, or we say it's a big C calorie. SI unit of heat is the joule. So 1 joule, we looked at this previously. It's 1 kilogram times meter squared over second squared, or calorie is 4.184 joules, or a big C calorie is equal to 4.184 kilojoules. It could also be a kilocalorie, small c calorie. So Q is heat energy, typically in kilojoules, joules, which means typically it's going to be kilojoules, but we can do it in joules or calories. Again, if it's less than 0, the reaction is exothermic. Heat is given off to the surroundings and it's on the product side. I know what we looked at previously. Q is greater than 0, the reaction is endothermic. Heat is added to the system from the surroundings, and heat is on the reactant side here. Well, here's an OWL question. So the next page, let's look at an OWL question in the beginning of this. I think there's 2 of them in a row here. And it depends upon the terminology here. And 4 moles of iron rust to form iron 3 oxide. Energy is evolved. If energy is evolved, that means this is exothermic. That means Q is going to be negative 1648 kilojoules. Now this is a reaction you can relate to. These are the hand warmers, the throwaway hand warmers that you buy, or the foot warmers, and all they are is powdered iron in there with sawdust. And when you break the plastic seal, you're allowing oxygen to react, and you get iron oxide plus heat, and it lasts for, I don't know, 6 hours maybe, right? Those are great. They're completely environmentally friendly. The only thing you're allowing to happen is iron is forming iron oxide. They're great. Throw them in your shoe or your boots or whatever. So is the reaction exothermic or endothermic? It is for sure exothermic. What is the value for Q? Include the sign. Will energy go on the reactant side or the product side? And it's definitely going to go on the product side, right? So that's how OWL starts out. Here's another one. When calcium carbide, CaC2. So this comes from is manufactured according to the following reaction. 465 kilojoules of energy must be absorbed. This means we have to put heat in. If we have to put heat in, Q is going to be positive 465 kilojoules. So we know that the reaction is endothermic. We know the value of Q, and it will go on the reactant side. And when they go in, they're always positive. So this one up above, we could put plus 1648 kilojoules here. And here we could go 465 kilojoules here. Okay. So that's 5.1. And again, I'll just kind of go through this terminology in the beginning. Let's look at 5.2. So now we're going to get into some energy. So here is the table from our book. So this is Cox, 9th edition, which is what the book we have, table 11, which is an appendix D on page A14. This is the heat capacity of some elements, compounds, and substances. So this will be specific heat. Now, your textbook uses this. They'll use a C here. They use SP. I'm just going to use a C. Look at the units here. It's in joules per gram Kelvin, but it doesn't matter Kelvin. If you increase 1 degree Celsius, you increase it how many degrees Kelvin? 1, right? So this doesn't matter. I won't use Kelvin. I'll probably use degrees Celsius. But if you're talking a mole, they have molar heat capacity, then is C with an N for mole. So let's look at some of these values for aluminum. This is the amount of heat energy needed to raise 1 gram of aluminum, 1 gram, 1 degree Celsius in the unit of a joule. So notice aluminum is double iron. Takes more energy to heat up aluminum than it does iron. It takes less energy to heat up copper, 1 degree Celsius. Gold even less. But this is the big one. Takes a lot of energy to heat up water. 4.184. It takes a lot. And the fact that liquid water is 4.184 joules per gram degree Celsius, it takes a lot of heat energy to heat it up, makes life on this planet all possible. How much energy goes into heating up water? A lot. It also makes it so that the lakes in the summertime, when it's 95 degrees out, the lakes don't get up to 95 degrees. So the fish stay alive. Takes a lot of energy to heat up water and a lot of energy to cool down water. But realize that we have a different heat capacity for this. Ice has its own specific heat. Water, liquid water has its own specific heat. So this would be H2O liquid. This would be H2O solid if it's ice. And this would be H2O as a gas. All different specific heats. Okay, so down below again, specific heat. I'll just use letter C. I'm going to put it in the SP. The energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. You'll see me write it like this. It will be in joules times grams over degrees Celsius. This is correct This is just like a multiplication dot. I don't know. Term specific heat means per gram. Let's go to the next page here. And then there's molar heat capacity. I don't know why it seems like OWL does some problems with molar heat capacities, but typically that's not used that much. So that's the heat energy required to raise the temperature of 1 mole then of the substance by 1 degree Celsius again. It's for a mole. All right, you can represent the energy required to raise the temperature of any substance by the equation Q is equal to mc delta T. Now, this Q can be energy in joules, it could be energy in kilojoules, and it could be energy in calories, small c calories typically. And C is the specific heat. What you're calculating depends upon your specific heat. Is your specific heat is given in kilojoules, joules, or calories? So the specific heat can be given in all 3 units here. And this is just the temperature change, T final minus T initial. So we do a problem like this. How much heat energy is needed to warm 250 grams of water, about 1 cup, from 22 degrees Celsius, which is about room temperature, to near its boiling point to make some spaghetti, 98 degrees Celsius. Specific heat of water is 4.184 joules per gram degree Celsius. So we are just going to do Q is equal to mc delta T. So let's just plug this in right here. My mass of water is 250 grams. Specific heat, that's my mass, right? My specific heat, 4.184 joules per gram degrees Celsius. For those that do not write in all these units, it is not going to go well, because this is where you realize what the answer is going to be in. This can be in kilograms, this could be in kilojoules, this could be in kilograms, this could be in calories. So if you write in these and don't take a shortcut, then you'll see that our grams are going to cancel out. Now we just need our temperature change to cancel out. And our temperature change is going to be T final minus T initial, which would be 98 degrees Celsius minus 22 degrees Celsius. And 98 minus 22 should be 76 degrees Celsius is my temperature change. And then my units of degrees Celsius are going to cancel out. And I know my answer is going to be in joules. And if I crank that through, 2 sig figs out of this, huh? Yeah. 2 sig figs gets us 79,000. Okay, 2 sig figs would give us 79,000 joules, which would be 79 kilojoules is probably what I was going to have. All right, example 2, page 217, number 9, I guess. The initial temperature of 344 gram sample of iron is 18.2. So let's put in, this is T initial. Let's put TI. This is T initial. This is a mass of iron. So I'm going to put MFE for iron. That's my mass of iron. I'm just trying to identify stuff as I'm reading this problem. The sample absorbs 2.25 kilojoules. So this is Q for energy. And we want to know what the final temperature is going to be. We're looking for T final. So we know that we are going to use Q is equal to MC delta T, right? Now, what I'm worried about, as I'm looking at this right away, what I'm worried about is this is in kilojoules. This is in grams. I'm worried about my specific heat. So I'm going to turn back to my table and see what units my specific heat is. Again, we have iron. So if I turn back, do I have iron on here? Yes. We have 0.449 joules per gram degree Celsius. 0.449. So let's flip over and write that down. 0.449. Specific heat of iron is equal to 0.449 joules per gram degree Celsius. So if that's in joules, let's change this right here to joules. Right here would be 2250 joules, right? 2250. So let's use that. So now we know our units are going to match. So let's start this out. So we had Q equal to MC delta T. So we've got 2250 joules is equal to 344 grams. 0.449 joules per gram degree Celsius. Final minus T initial looks like this. Now, how do you solve this pig? What's the quick way to do it? I would probably take the 2250, divide, right? That'd be the way to do it. Take 2250, divide. I know my units are going to be correct. I'm just looking here. So my units now they're accounted for. If you take 2250, divide by 344 and divide by 0.449, then you're going to end up with 14.6 degrees Celsius is equal to T final minus 18.2. Better highlight this because it looks like I got a little bit. I could use just a little bit more room here. Then if we add 18.2 to both sides, we're going to get T final here. 32.8. All right. Again, just make sure your units are going to work out. Let's set up this last problem. We're not going to have enough time to solve it, I don't think. But we need to set this up. So there is a trick to figuring these questions out. So follow along with me on this. In an experiment like that shown in the figure, 88.5 grams of iron. So let's actually go, this is 88.5 grams. We got to fix that. At an initial temperature of 78.8. Is placed in a beaker of water containing 244 grams. So let's change that. 244 grams of water down here at 18.8. When equilibrium is reached, now, if you drop this in here, obviously the temperature better go up. When thermal equilibrium is reached, what is the final temperature? We're looking for T final, and that's going to be the same as for the water and the metal, right? Thermal equilibrium. Now, here's how you want to set this up. This is not the way the textbook does it. You want to set it up like this. Divide this. Let's keep this organized as best we can here. We're going to have two columns like this. We're going to go like this. And we go Q lost. Heat energy lost is going to be the heat energy gained. Conservation of energy. Now, what is losing heat? What is losing heat energy? Iron, right? The iron is going to get cooled down. So we know that the iron is losing heat. Q lost has to equal Q gained. And this, what's going to gain heat energy is the water. Okay. The mass, let's just identify everything. My mass of iron is 88.5 grams. My T initial of the iron, 78.8 degrees Celsius. My specific heat of iron, 0.449. My mass of water is 244 grams. T initial of the water is 18 point Celsius. My specific heat of water is 4.184 joules per gram degree Celsius. I'm looking for T final. T final of the iron equals T final of the water. We're just going to call that T final of them together. We'll set this up. We want to set this up as Q loss equals Q gain. That's going to be the mass of iron, specific heat of iron, change in temperature of the iron equals my mass of water. Temperature of the water. So we are going to get to the point where we can put this in. If you're going to work on this in OWL, we are at the perfect spot. Please pay attention now. The trick to this. Let's put the numbers in. 5 grams. For 9. Here's the key to this. Have to make the temperature changes positive. You have to make the temperature changes positive. So sometimes I'm going to go T initial minus T final. Sometimes I'm going to go T final minus T initial. You have to make the temperature changes positive. Now, make this positive. Is the iron, which starts out at 78.8, going to get hotter or colder? Going to get colder, right? So to make this positive, I'm going to do 78.8 degrees Celsius minus T final. Over here, my mass of water, 244 grams. Specific heat of water, 4.184 joules per gram degree Celsius. This is going to be T final minus T initial, which was 18.8 degrees Celsius. Again, make your temperature changes, make sure, because T final is going to be higher than 18.8, right? You have to make the temperature changes positive, then it all works out. There's just solving that for T final. And make the temperature changes positive for those. On the quiz, if you looks like 1 through 7 on this quiz matches up perfectly. So on the chapter 5 quiz, if you can take a look at 1 through 7, that'll get you in perfect spot. You should be able to work on the OWL chapter 5 part 1, start poking around into that. Chapter 5, is there a part 1 and a part 2? There is, yeah, there's a chapter 5 part 1 and part 2. So start poking around in chapter 5 part 1 in OWL. We'll answer final quiz questions from chapter 4. And we'll be in good shape. All right, have a great day, you guys. The roll sheet did make it. It's right down here. So if you haven't had the roll sheet, it's right down here.